Hello, this is Dr. Mohamed Nezami again. Okay, I didn't anticipate on part three being this long. Um, and let's just finish the rest of part three, and I call this part 3B. Um, we were talking about the design of an LNB, just like this, like I showed in the block. You can, just in case if you're watching this part, please, we are continuing the series on KKA band, SATCOM, low noise block receiver or down converter. This is part one here, part two here, and part three here. And now I'm just finishing the rest of part three in a separate part due to a little glitch in the software. So, okay, so we were talking about this. I proposed to design a single LNB for dual bands to cover the entire band from 17.2 to 21.2. And the way we do this is we have two separate LOs, two separate image rejection filters, and a common IF path. Okay, and that's basically I showed that in here, and this is the system view implementation. So we basically come in here. Let me, in fact, just switch over here to the system view. So I have a signal generator in here that generates a Ka band signal right now. As you can see, I'm putting some noise floor, and I'm putting two signals. I'm calling one is the FRF high and FRF low, and they're both at minus 90 dBm. Okay, and FRF and FR low, I'm defining them in the equation part. Basically, they're right here. This is a MATLAB nomenclature that you can run within system view. So you could literally go here and say, I'm going to show you the design variables, and you should be able to see these in here. Okay, well, right now I'm not running this. I need to refresh it, but that's how you would see them. In any case, so we have, let me just close. So, okay. Okay, so let's just get back to here. So basically starting out here, the LNA right now is specified at these values. And what I'm doing right now at here, this is what we're going to design discrete and discrete transistors. So right now what I have is these switches that are controlled by the state, where you can come in here and literally just say one, for instance, and it would switch over to the other side. Okay, as you can see here. So let's just not do that because this is for band one. So band one go through this filter, and this filter was designed in here, and you can see the specification on this filter. It's going to be, I'm going to have to design this in the HFSS. So this is a band pass filter using Chebyshev type 2. I'm allowing the insertion loss to be 2 dBs, and the F low and F high is from 16.8 to 19.6. This filter response basically is this here. So that's what you get this here, which we're hoping that we're not going to get rejection of 97, 100 dB down, but we should, because physically we're limited by the coupler through the substrate. So, but in any case, theoretically, that's how this filter should behave. So I'm using that in the front end. Okay, just zoom in on. Okay, and then the mixer, we did go through that model. And here's the IF stages in here. Okay, there are two filters in here. These filters, I got the S parameter models. They're basically right here. These are the S parameter small signal models for all of the devices that are now I have a mimic amplifier in the IF stage. Basically, we can go to the here is the model for it. I just grabbed just a few points, just between 800 and 2400, 2950. Okay. All right. So And then what else? Let's see. The LO section I'm going to talk about in a separate part. Okay, so I ran this, and basically what we can get out of this is you can go to the budget link, and the budget link will show you the progression of the accumulation of the desired channel power. I'm just I'm putting in the signal generator, which is the red curve here. So starting out minus 90 dBm, we start out, there's the LNA, so that should be 30 dB gain, and then it stays passive, and then so on all the way. And you can see the noise figure in here is 1.023. The overall gain is 68. And then I ran most of the stuff. But what I did next is where we stopped last time is I wanna basically come in here to this generator in here, and the FRF low, okay, this signal in here, which is right now enabled. I start a sweeper that would sweep that parameter, which is FRF low, from 14 gigahertz to 25 gigahertz, okay, with 100 points in there. So, and then, of course, the power level is still set to minus 90, which is defined in here. Like I did define it in here. That's the FRF low, that's enabled, as you can see. The other one is not enabled right now because I don't want to have two carriers in. So basically, I'm setting this to minus 90 dBm. And what I'm going to do is it's going to run and sweep the front end completely, and that takes a long time. That takes about an hour sometimes. So, but I'm going to just get to the right point. Let me show you the noise figure and gain versus, okay, so what this is here is the cumulative noise figure and the cumulative gain. That's these guys here. Let me take it here. Okay, so basically, as you can see, here is my RF output, the conversion gain, and what you can see here, it's between 65 to 70 with a 5 dB variation, gain flatness. And then the noise figure is the same way here, as you can see. So it's pretty good right now. So, okay. So basically, and then of course, I through the sweep, I am extracting the sweep data using these using these command lines in here to get the output power saturation, the desired channel power, and the input P1 dB compression point, and that's what I'm displaying in here. And you can see that in band in here. The nice thing about this, I'm trying to see out of band if it gets compressed at all. And it doesn't. It would take, I mean, you would have to smoke the front end to get any compression. Except in band, of course, it's pretty good. That's according to spec. Same thing for the, let's see, the input 1 dB compression point and the output saturation. So this is good because you can see in band, out band, and all that stuff. All right, so next, what I'm going to do, I'm going to come back, repeat the same thing, except right now, what I'm going to do is I'm going to go back to the signal generator in here and disable the low band signal and enable the I'm sorry, enable the high band test signal and disable the low band test signal, which okay, so I'm going to do that. And then of course this one in here, I'm going to switch the state, so I go to the other filter. So we're going to go back to state one, that's there. This one also. So I'm going to get that to go to 1. Okay, and then I'm going to come back in here, and in this one, I have to go back to the other one. Now, you might ask, why are you switching since I'm disabling this, okay? And this has something to do with the system view noise figure computation. For some reason, it didn't like multi-input, multi-output. So right now we're here. So we're gonna enable this, okay? And then disable the low band test signal, okay? And when I run this, of course, it's gonna take a while, but basically, just to go through it really quick. Okay, so this is the low band. Oh, this is low band. So this is the high band. So we start out the high band in here, like I just did. Okay, switched over to here, switched over to here. And this is basically what we get. Very similar performance, just fractions of a dB difference. Okay. In compliance, the IF level, pretty good. Okay. The compression, power compression, power out versus at the power at the IF versus the Ka band input at the RF. Same like for the conversion gain and the image conversion gain. I'll define that as well. That's valid to say so. And then, of course, the sweeping, we do get exactly the same thing. Okay. So basically, for the high band and low band, it's the same thing. So what I'm going to do next is to see the impact of this filter in here. As you can see now, the this single sideband down converter is designed so that you can utilize it actually without a front end filter. So what I'm going to do is come in here and disable this as no, not open, but as short. Okay, and then let this run through without a front end filter and see what happened. And that's basically what's in here. So the blue curve is what we just got with that filter in there. And then the red curve is the one that we got with the by disabling this, removing this filter in the front end. And as you can see clearly, the image rejection is just the single sideband specified image rejection, which is if you subtract this 2A is, let's say 40 from, this is 1A from, okay, this is 2A from 17 from 40, so which is in the middle 20s, okay? And that's exactly what we were supposed to get anyway. Because if you go back, let's see, if we go back to the mixer itself here, and let's just see what the image rejection that is specified. Image rejection is 35 dB, okay? And it deteriorates down all the way to 19 dB, okay? So that's what we get, and as a function of frequency. Okay, so up in the upper band, it becomes in the 20s, okay? So that's what we would get. Okay, so this is, I apologize for making this a separate part, but the computer quit on me, and I don't want to go back and start editing and gluing videos together. So basically, this was, ladies and gentlemen, I thank you again. This is Dr. Mohamed Nezami. Thank you again for tuning in. This is the second part of part number 3. Please go ahead and log back and check the first portion of this, which was the largest part. So again, back to flashing an advertisement by you. I'm basically a freelance consultant. I work at this rate here, very reasonable. I operate out of Jerash, Jordan, offshore to the United States and Europe. I have many clients that are very satisfied with my design services. Please call me, email me at this number. If you'd like to get in touch, if you have any any design work for high frequency and microwave flash it by me. Let me see what you got. My consultation is free for the first several hours. I could basically go over what you have and give you a reasonable rate. And I work with you from concept all the way to fab files, to Gerber and PCBA fabrication files. So today, ladies and gentlemen, we talked about the design of it. So what are we going to do next? What are we doing next? I think I should have a slide on that. Here we go. Okay, so what do we do next? Okay, so here we are. We proved system level wise that this will work, will satisfy the requirements. I first of all have to go back and construct the mixer with the actual 90-degree hybrid that I have, because I just don't have the hybrid that they have used to measure the performance of this mixer, of this quadrature down converter. So I need to build that model, just verify that with the hybrid that I was looking at earlier, or some variant of it. Let me just show you that one. This part here, okay? This part here, okay? Or some other variant of this. And this is being made by lots of companies in the United States and Korea, and some in Europe even, and in India even. So I'm going to take that and hopefully just verify and make sure that I'm still got that going. So the first thing we want to do, then the next thing is we still have the LNA as a discrete, as a black box right now. We need to design that discretely, and that's where the design now had to shift over to the advanced design system, CAD tool, ADS, to design that, because that's an active signal design. So I picked already the devices. You might recall they were the NEC or the CEL or Renaissance. They changed like 5 different companies, the same part though. One of the misfit devices that's used for K, which has a noise figure F-min of like 0.8 dB. Okay, so I need to design a single stage, cascade 3 of them together, so that I can achieve this performance in here. The next thing I want to do then is this is the image rejection filter. Has to be designed like this, and this talks about how I have to insert back a 90-degree quadrature hybrid in here. So, and then make sure that the overall performance is okay as far as image rejection. And then, of course, I've got the LO. This LO is a fixed dual signal, not dual band, dual signals, because this I would have to run it at one time at 9.125 and 8.125, which is the same chip, except I'm going to use a little microcontroller in here with the synthesizer programming parameters, register values to set this PLL chip every time you power this to a specific frequency. And there's got to be a command that comes in and tells this LNB switch over to either low band or high band. And currently, commercially, the cheap ones that are for the home devices, home direct TV, they use either the DC supply that comes in here can vary. Actually, they can vary from like 18 volts to 15 volts, and that doesn't impact the regulation section, which regulates from say 15 or 18 down to like 3.3, 3, 1.5, 5 volt. That doesn't change because it's fixed. But what it does, you can utilize that as a switch to switch between bands. Now, in some of these cases, they have the DISIC, which is a standard, I think it's 122 kilohertz signal, that either its presence or its absence means you can utilize that as a way to switch between bands as well. Okay, and that's a standard way. Or you can have a manual switch if this is on, or somehow some digital signal switch. If this was to be used with flat panel, and this would be integrated along with the phased array antennas, then obviously that would be just a digital signal switching over, controlling these switches. This will switch, this switch, and that switch here. This switch here may not be a switch. I designed one KU band system where I didn't use switches in here, but what I did use is turn these on and off, okay? And they were basically combined with a two-way splitter in here, just to maintain impedance matching, okay? Just like I would do here, I disable this, meaning turn this off, turn this on. Okay, so we need to design that. So in the design PLL, the slope on the IF, that really cannot do anything about, because this device in here is mainly for what's causing that slope. And that slope is going to get exaggerated by the slope from these filters as well, because these will tend to have a downward slope as well, because and even the LNA itself. So really, to counteract this downward slope, because this chain deteriorate in frequency, the gain as a function of frequencies go higher and higher. We need to undo that, and the way we do it, I'm going to have a small passive suction in here that will, if the gain is going this way, that one will be going this way, so that the overall is equalization of the gain as a function of frequency. So that's very simple to do, and you can look that up. People have written about this, and it's well defined and illustrated in radio frequency design books. Just type gain equalizing for amplifiers. Okay, so and then the 90-degree hybrid, of course, we have to get it to perform well between 950 and 2950, because as you can see, the one I saw in the industry didn't really achieve that. I mean, the one I picked from the NRN1, or not NRN, TTM nowadays, it's hard to get all these. In the United States, there's so many acquisitions of companies for semiconductor between RF component makers that they changed like 5 times ownership in the last 5 years, a lot of these components, and we still refer to them by their owner, or what the manufacturer name was 10 years ago. Okay, ladies and gentlemen, so I would like to thank you again for tuning in, and I'll be looking forward to you on this design, continuing this, and I will see, even though I put these things in sequence, they might not be like I mentioned them here. I might actually, change the order of these as I see things appropriate. Okay. Well, thank you, ladies and gentlemen. Have a good day, good night, good morning, whatever time it is where you are around the world. I appreciate your tuning in. Thank you. Please subscribe to my channel and support if you can. Thank you.